Welcome back, everyone, so far. We'll get started in just under a minute. Hello. No worries. Someone went into the wrong classroom on accident, if you're curious. Looks like we could get started. Welcome back, everyone. So we're moving through the week, and we're definitely getting to a point where the course is hitting its stride. And pretty much every one of these blocks, weeks 1, 2, 3, 4, they're just going to repeat in this order that you're seeing so far, where you'll have the reading, a due date once we have finalized that section, the solutions after we've completed as well. At the very bottom will be the quiz that's going to be due a week away. And if you look at the prior block, that'll be the upcoming quiz. So pretty much we're just going to get in a habit of posting and presenting the material in this kind of way. With what we have going on so far in the announcements, quiz 1 will be due tomorrow. Quite a few people have already handed in the quiz, and you're always welcome to submit them early if you just would like to finalize that to get it off your to-do list. And we'll be finishing off Unit 2C before very long in this class meeting and starting off the Unit 3A, moving into Chapter 3. Not a whole lot of announcements today, but any questions at all, folks, to get us started? Okay, well, quiz number 2, we'll look into that one when we're back on Thursday, but usually, like I mentioned before, I'll be posting these a day early. They'll be considered officially assigned on a Thursday and then due on the following Thursday. And the other thing we'll probably talk a little bit more about when we come back tomorrow, next class, is the exam one. Before we get into week 4, I'll be posting the exam information and then sending everyone direct instructions for how to schedule the exam. But again, we'll talk a little bit more about that when we come back on Thursday's class. So far, here's where we left off. In Unit 2C, it has a lot of pretty challenging problems, and some of these are not easy to start unless you maybe have looked into the problem quite a bit, have a really creative mind for problem solving, or maybe you read the examples like I did in the book, so that gave me a good idea how to attack some of these kind of problems. The idea with every one of these problems is they're meant to tie in somehow, some way, with the author's problem-solving hints 1 through 8. We're not going to necessarily hit on every single one of the hints exactly, but a lot of these do match up with some of the problems. So if you say scroll through here, I didn't put anything on example 3, but I felt like it was not too different with what was going on in example 2. I showed one solution, but there could be a different way to get the same value. And the idea with this one was to try to take something complicated like this corkscrew spiral of a ribbon being wrapped around this mailing tube and make it a simple or similar problem. That was our idea. Just cut the thing and flatten it out to a rectangle and then analyze one strip, multiply the results by 5 to get the total length. Situation. Sorry, looks like an open mic. On the current one, here's the new situation. So imagine you have 40 meters of fencing and you're going to make a dog park. Let's hide part B for the moment. It's going to be rectangular. And we want to know which rectangular shape will give the dogs the most area to run. That's a pretty interesting question to start out. And just like all the other examples, it might make us feel kind of like this is a wide open question that doesn't really have a direct start to think about right away. And the idea for this one, as far as the problem solving hints go, would be this one is a pretty big wide open question right away. Some people might know the answer to this, so if you happen to know the answer, don't hesitate to shout it out. But the big hint on this one is if we can consider, let's say, hint 4 and 5 seem so identical in a certain sense, but let's think of this as hint 4. consider simpler, similar problems. So instead of worrying too much about the optimal shape right away with the most area possible for the dogs, let's do this problem out of order. Part B is just a direct, particular situation, a similar problem, and we're asking if you make the fence 12 meters long, 8 meters wide, can we in fact do that? In other words, would we use up the 40 meters of fencing? And what would be the area in that scenario? If we can solve part B, this is a simpler problem because it's more direct. It's telling you exactly what to do. Determine if you can fence this out with 40 meters and what is the area. As we solve part B, it might give us some intuition on what's going on in part A. And if we're still not sure, we'll do this again. Consider just another similar problem in part C. Well, let's start off with the major quantities. We have 40 meters of fencing, and we're going to think of that as being the perimeter. The amount of area that's going to enclose the rectangle that we're looking into. A rectangular is kind of an interesting word because rectangular we usually think of as having a length and the width. And we usually think of the length and the width being different, but they could in fact be the same, just depends on the problem. Here they're different. There's a 12 meters long and 8 meters long. So our rectangular park is going to look like this. I'll let that be the 8 meters. And proportionally, that's about 12 meters to my eye. But again, these diagrams never have to be perfect. Just to convey the information is their goal. So I have, that's kind of out of proportionality by a good amount. Let me try again. So I want to go 8 meters high, 12 meters long. I think it's a little bit closer. So this will be the width, 8 meters. This will be the length, 12 meters. And the question is, would this work? Can we make this fence with those dimensions? In other words, would we use up all 40 meters for the amount of fencing we have, the perimeter? Well, this one's not too bad to answer. We can say perimeter would just be the 12 meters this way, 12 meters going this way. So those two lengths, 2 times the 12 meters. And the same idea, take the 8 meters going this way, plus another 8 meters, or just 2 times 8 meters. And let me backtrack just a bit to go like this. M3 meters plus 2 times 8 meters. We work out this multiplication here, we'll find that the perimeter is 24 meters plus 16 meters. Adding those together would give us 40 meters altogether. And so we would say to this question, yeah, if we have 40 meters of fencing, these dimensions would work. So we'll say, yes, we can make this fence. So the next idea is we want to determine how much area we're going to come up with if we went with these dimensions. So we'll just take that length times the width. Area is going to be 12 meters times 8 meters. So that's going to be, let me see, 96 meters squared. You know, for a night class, arithmetic is the first thing that goes out the window when you're getting tired. So no harm double checking that just to make sure everything goes right on paper. So it's good to have a calculator always kind of nearby, ready to go for this class. And so we addressed both parts of the problem. We have the area, and we answered yes, we can make this kind of fence. The perimeter would be 40 meters, using up all the available material. And the dogs will have 96 square meters to run. A meter is approximately 3 feet, so that's a pretty big area for the dogs. But this is not the whole end of the problem. Really, the major question, that one at the very top, was which shape gives the dogs the most area to run? So we still need to come back to that question there. Anyone have any ideas on what would be the most optimal shape?
A square.
Yeah, good call. Absolutely, Malik. This one would just be a complete
Excuse
square.
me. Excuse me. My bad. It's pronounced Malik.
Malik, gotcha.
Yeah,
So
all
thinking,
good.
Malik,
All good.
now, if we go with this square, that's going to be the absolute optimal shape on this one. And that's the weird thing about this problem, right? When it says rectangular, I would myself be thinking, we don't mean a square. Rectangle has a different length and width. But no, a square is a particular kind of rectangle. And so by just the weird issue going on with the problem, let's try this hint on it, include this one in. Thinking in terms of different things, a square works for this, and that's the alternative pattern of thought, I guess, is a great way to think about this hint. A square also works. And remember, we said that this has to have the most possible area. So let's check this out. If we go with a square, as Malik suggested, shape should be, let's imagine this is a perfect square. And you could use L for the length. Oftentimes for squares, people write out S for side length. What would you all say the side length would have to be in this case?
10.
Yeah, absolutely. If we're coming out with 40 meters, we need to use 10 here. So now the perimeter is just going to be the length around, but that would be taking 10 plus 10 plus 10 plus 10. That's why the formula is written as just a simple 4 times 10 to abbreviate that. So this will be 4 times 10 meters. Forgot the unit down there, M for meters. And so this would give us a perimeter of 40 meters altogether. So that dimension would work. And we said it's going to give us the optimal area, so we're expecting more than 96 meters squared. Let's check this out. Area is going to be S times S, or just S squared. So take 10 meters times 10 meters. This gives us 100 meters squared. And yeah, that definitely beats out the 96 meters altogether. And we can keep trying to see, is there any way to beat this? But the only thing you can really do is, if you make this bigger, you'd have to make one of the other dimensions smaller, and it'd be essentially this problem. If you make this smaller, you're making the other dimension here bigger, and it's back to one of these. And you can try a whole bunch of different kinds of problems and find somehow, some way, the square does the job. That's going to give us always the most optimal area. We still have to answer part C, because imagining this is a problem in my lab, it's going to ask us all 3 questions. But sometimes you don't have to do these problems in order. It's possible and conceivable that a MyLab problem in this section asks you the hardest part first. And if that happens, just go for the easier ones. Go for the lower hanging fruit that we can do immediately while we're thinking about the larger question. So let's finalize part C, but first, any questions on part A whatsoever?
Yeah, it's a wait. So how do you answer that? I'm kind of confused. Like
That's a
it
great
says
question.
like it says what shape, like all it says is what shape gives the dogs the most area to run. So how do we get all the way to 100 square? Like I know how we got there, but can you just go through it one more time?
Yeah, I see what you're saying. The question here, if it was in my lab, would probably have one of those things where you pull down a tab and give certain answers. But to answer this part directly, I think probably what we would have said is a square gives the most area because if we look into, say, setting up a square with 10 meters, we get the right amount of perimeter length, 40 meters, and the area comes out to 100 meters squared, which is going to beat out any of the values that we could ever conceive in the prior parts. So I'd say to directly answer the what shape part, we would just say a square, because this here shows we use the right amount of fencing. And this last part, just finding the area as 100 square meters, that's kind of an awkward way the question was written. It didn't actually ask for the area, right? It just wanted to know what shape. So really, this would be the total answer to this whole question. If this was, say, a question on a quiz or exam, saying a square really does the job there. It answers the question verbatim, and everything below is just checking if the perimeter makes sense, if the area is really exceeding anything we do below. But does that make sense with that question there?
Yeah, I get it now. I appreciate you.
Yeah, you bet. Thanks for asking about that. And
Uh,
yeah, sometimes these questions, they're in my lab and they look a certain different kind of way, where sometimes it's like a multiple choice thing going on in my lab. Sometimes there's a little tab button that you go and select different values. But then putting it down on paper, yeah, sometimes these have an awkward feel to it. So thanks for asking about this one. Other questions at the moment? Okay, just to get another verification that this really is the square giving the most area, and this is like the work below that shows that makes sense. Let's see if we try a different shape. We're going to go 15 meters long, 5 meters wide, to see if that can possibly improve our area. 15 meters long, 5 meters wide. So we're going 15 meters long. Let's let that be the 15, and about a third of that is the 5 meters wide. About like that to my eye. Again, it doesn't have to be perfect. Seated a little bit there. Now imagine it's a perfect square. We have width is 5 meters. Length is going to be 15 meters. And the first question is, can you make this work out with your available 40 meters of fencing? So the first thing we'll do is compute the perimeter to directly ask that first question, answer that first question rather. Perimeter is going to be twice length plus twice width. So it's going to be 2 times the 15 meters plus 2 times the 5 meters. So we'll get 30 meters plus 10 meters. We're about done then. We get 40 meters altogether. Double checking, that works with the amount of material we have purchased. And so we can say, once again, yes, we can make this fence. So that part addresses this part right here. Can you make the fence? Getting 40 meters directly answers that as a yes, like in the last problem. And now we wonder what's the area on this one. That's another one of these computations down below. Take the length times the width. Let me zoom out just a touch to fit this in. So now area is going to be, let's put it in the formula first. It's always a good practice. I mean, this is not the worst formula, but when it comes to memorizing formulas, right, just writing it down on paper like this first before throwing in the values is a great way to memorize them. So go 15 meters times 5 meters. Let's cite that calculator to make sure we get this on dead even. This comes out to 75 meters squared. And that's kind of interesting. Between parts B and C, let's look what happened. Here the dimensions were kind of close to each other, right? It was more squarish in part B. We had an area of 96 meters squared. But when we made it less squarish, this is now a pretty long and short width, we got less area altogether. So the logic really does seem to pan out. It seems like you improve your area, the closer and closer you make both the length and the width equal to each other. If you make them dead on equal, the square, that's going to give the optimal area on this one. Not something I necessarily would have guessed without going through this whole problem like we just did. And so that's why it fits in one of these kind of hints here from the section and problem solving hints. You can break it down to just different kind of scenarios, see what's happening as the shape changes. Then you can get a pretty good hint on what the optimal shape might be for, say, a scenario like this one, finding the most area. Well, any questions, folks, on getting through this one? Okay, let's try out one more then. This is the last question to finish out these notes. And again, one comment I made before when we were just looking into 2C is the reading is pretty challenging on this. So don't let yourself get discouraged if you feel like some of these problems are just kind of really wild out in left field. something that you might have felt like it had been really hard to come up with a solution with. Some of those were kind of what we did in these notes. But now that we saw how they go, they're going to be pretty similar kind of questions you'll see in the MyLab homework as well. And as far as exams go, we're not going to try to ask the trickiest, strangest problems on exams. That wouldn't be a really good way to assess your understanding of this material. There'll be some of the more faster routine problems that you might saw in this section. And here's the last one for the notes. It's kind of a weird kind of problem, but there's a real honest to goodness mathematical principle behind the idea that we're going to use on this one. So it's probably a familiar scenario. You're reaching into a sock drawer that has 20 white socks, 30 black socks, 13 red socks. So you can imagine maybe that's an interesting sock drawer. Yours might be different. Imagine you're doing this in the early morning. There's no light whatsoever. It says, without looking, how many socks do you have to pull out to be 100% sure you have a matching pair? Well, you could pull out all of them, right? That would do the job. Just empty the whole drawer. You have a matching pair. So there's a lot that's unsaid when it says how many. The real question here being indicated is find the least amount that guarantees a matching pair. Since if we just completely empty the entire sock drawer, we're just making our morning more complicated at that point. Anyone see what would be the answer to this kind of problem?
Wait, can you ask the question again?
Yeah. So in this scenario, it's a weird situation where you have a sock drawer with the 20 white socks, 30 black socks, 13 red socks. What is the least amount of socks do you have to pull out of that drawer to be 100% certain you have a matching pair?
Um, 6.
6 would do the job for sure. But it turns out you could pull out less than that. Anyone see what would be the smallest number that would work? Echo has a good point here. You find that one lone sock that isn't folded. Let's imagine for this problem that you didn't fold your socks. You just dumped them in the drawer completely unfolded. They're thoroughly mixed. So nothing's been paired as well. So 20 individual white socks, 30 individual black socks, 30 individual red socks. If you pull out 6 socks, you absolutely will find a matching pair, but we can find a lower number as well. Amy says 3. 3 might not work out. Let's imagine this random scenario. So let's start writing out some numbers. So for 6 socks, this will absolutely guarantee there's a matching pair. But for 3 socks, now this one's kind of iffy. This one, it depends, right? If you randomly grab 3 socks out of this drawer, it's plausible you grabbed a white sock, a black sock, and a red sock. No matching pairs. So here, if all socks are different, there is no matching pair. Echo says 4, and yeah, that actually does it. It's kind of a weird problem, right? If you grab 4 socks, but you only have 3 different kinds of socks, a pair is guaranteed. So that's the weird observation in this kind of problem. This one's kind of hard to say which problem solving hint are we using in the first place. Maybe hint number 1, because as the instructions said, if this is a real exam problem, that works. 6 socks does the job. But when you do this one in MyLab, they're going for the minimum. They just never said it in the problem. So we're trying to optimize this one and find the minimum amount possible. And 4 really does the job. So what else could have been going on here? Maybe this one, alternative patterns of thought. It's hard to say exactly what we'd have meant by that hint, but this is definitely a weird math problem in a certain sense. Here's the idea behind it. It didn't actually matter so much how many white socks there were, black socks or red socks. What actually matters the most is, well, there's more than two for each one of them, so you can actually get a pair, but also there are k equals 3 types of socks. So you are absolutely going to have a matching pair if you grab 6 socks. Once you've grabbed 3, the fourth sock that comes up, it can't be a brand new type of sock because there's only 3 kind. If you grabbed 4 socks and nothing matched, well, there's more going on in this drawer than what we specified here. So the optimal answer is going to be 4 socks. This one also gives a matching pair because 4 is greater than that number 3, which was equal to, we just use a random variable k, the number of socks that we had in the drawer. So this one works as well. Again, for an exam question written verbatim the way it looks like here, 6 socks, 7 socks, or even, let's count them, there's 50, 63 socks, that would definitely work. That's emptying the whole drawer. But the one they're going for in my lab will be this one. I forgot to pluralize that. 4 socks. Will definitely guarantee a matching pair. And this principle works with anything. It doesn't matter if you're talking about socks or types of coins in a drawer or the number of different kinds of cars in an auto dealership. If you count the number of types you're looking into to get a match, you just have to put in a number 1 greater. And the first number that exceeds the number of different types will be that minimum number that gives us the match. And this whole principle, if you're curious, is called the pigeon hole principle. So it's just a weird mathematical fact that ties in with this problem. Well, this one was pretty different compared to all the other ones. And all the other ones, it felt like we were computing something. This one was more just logic on its own, getting to that conclusion here. But any last questions at all, folks? Getting to that through this last problem here. Okay, well, thanks for your questions, suggestions, and thoughts on each one of these problems that we were getting through. Some of these are a lot more challenging than others. So when you try these out in the MyLab homework, come back here to the notes to see what we did. We'll have pretty similar problems that were solved here. And by the way, if you ever go into MyLab to do a homework set and you feel like there's a problem inside of MyLab that's just wildly different than anything we did in class, don't ever hesitate to ask about it. I'm happy to spend some time in class looking into any kind of questions that could come up in MyLab. That might be just a great way to start out class, and you're possibly helping quite a few people that might have been struggling with the same problem. So never hesitate to ask, even directly about MyLab questions. But we got through this unit. The reading here again is tough, so don't get discouraged. These will be the similar kind of problems in the homework. And if I ask an exam question directly out of that section, it'll be one of the more routine problems that's not going to make the exam overly long. So probably nothing about a ribbon being wrapped around a mailing tube. That was kind of a wild problem. Some of the more direct questions will be the ones that are fair game on a real exam. Well, we're moving on to the next chapter. Unit 3A is uses and abuses of percentages. Let me just tidy up these documents. So here's how chapter 3 goes. We'll be doing a lot with percentages in these sections as we're going from section to section. The overall context is numbers in the real world, but percentages in some sense are a great way, a great key to start looking into different kinds of interesting numbers we're going to come up with. Some numbers are just so large, like if you ever say something along the lines of 10 trillion miles, it's really tough to really wrap your mind around that. Or say, an example in the book, say the federal spending sometimes allocates $1 to $2 trillion for a single thing. And that's a really tough number to really put in context. What would $2 trillion even look like? How can you wrap your head around that? But thinking in terms of percentages first is a great shortcut to getting to those larger questions in the very next section. So here we're mainly just reviewing percentages, seeing how they come up in different kinds of contexts. But example one just starts off with just a quick math refresher on percentages, getting used to these kind of numbers. So all we're doing in example one is taking a number that's provided, it'll either be a fraction, a percent, and I guess another fraction on the third part down below. We'll express them as a fraction in its simplified form. So there'll be 3 parts to every one of these problems. We'll also express them as a decimal and as a percentage. If necessary, we'll take our decimals and percentages and round them to 2 decimal places as necessary. So let's start off with part A. We have a fraction, there's no context, so just a generic math question on this one. 17/23 is a fraction. We have to simplify it, but we're done. These are prime numbers, so this doesn't reduce whatsoever. This is already in simplified form. So let's say here, 17/23 is simplified. So we can move on to the next portion. We now want to write this number in decimal form, and there's various ways to do that. You could, if you're so inclined, you could start long dividing and get the value. But for this class, we're using the calculator quite a lot. So this problem, you're encouraged to just take this, drop it into a calculator, and write 17 divided by 23, and there's our decimal number. We're rounding this to 2 decimal places. So let's take a look. The second decimal place is a 3. This one then rounds up to 0.74. So that's our decimal number. We can say 17/23 is 0.74 as a decimal number. So this is the decimal form, now approximated. And that takes us to the new thing. We want also the percentage form of the same number. Well, that takes us to the definition as well. Percent is just literally saying per 100, where cent itself is meaning 100. I think I have something there to help us with that. Somewhere in the notes, I think it's down. It's really just one of these prefixes that's coming up once again. Centai, well, meaning 100. Here, percent means per 100. So in either way we think about it, we're just dividing by 100. 10 power negative 2 is just 1 divided by 100. So when we go to write out the percent form, we're just putting in a denominator of 100. And we don't have to work too hard with that either. This one would be another fast calculator problem. So take 17/23. Here it is as a decimal number. If you go times 100, you'll get 73.91, and that's our percentage. We're rounding this one to 2 decimal places, so it's 73.91 as a rounded percentage. 73.91, or let me write it this way. 17/23 is also, sorry, let me try again. 17/23 is 17/23 times 100%. Let's double check the calculator. When we did that, we got 73.91. So this is 73.91. We just throw in the percent symbol to write out as a percentage. So there's the percentage form. So any questions at all, folks? Getting the percent out of this one?
I have a question. If you
Yeah.
were to take the decimal form, so 0.74, and then just multiply that times 100%, you would get 74%. Would that be also a correct answer, or no, we have to take it from the fraction form?
That's a great question on this one. I was thinking about that as we were looking at these two numbers. I believe MyLab wants that one right there by the red dot. They're really picky. But I see what you mean. If you rounded once right here and you're just going off that level of precision, if you did this one as, say, a quiz problem or exam problem and gave me an answer of 74%, I would be completely happy with that. I wouldn't be that picky. But for the sake of MyLab, it's probably a good idea to be really, really verbatim and literal. When it said round the percents to 2 decimal places, MyLab really means go 17 over 23, then go times 100. It wants it rounded in that kind of way, which is kind of annoying in a certain sense. So watch out for that one issue. This is more blunt rounding, and this is a lot more fine rounding. Rounding the percent is not the same as rounding the decimal, in other words. Does that make sense with that question there?
Yes, so just keep it in it, just go with the original form for each calculation.
Yeah, exactly. If you always start off with a fraction, you'll be able to hit all 3 parts just fine without any kind of worries of weird rounding issues. Absolutely. Any other questions at the moment with this one? Okay. Well, just like the problem says here, 73% means 73 parts out of 100. We have 0.74. That literally just means 74 hundredths. So we could write that as 74%. Or the more accurate figure is the 73.91%. But either way we look at it, say looking into this quick example here, 73 parts out of 100 would be 73 divided by 100. There's its decimal form, 0.73. But if you want it as a percentage, you always have to go times 100. And that brings it back to the 73% we see right there. So this part right here is about one step in the calculator that's sometimes kind of vague when you're thinking in terms of the the definition. It seems weird to say a percent is a ratio with a denominator of 100, yet we multiplied 100% into the numerator. It almost seems like the logic is backwards, right? But really, this is just converting. 73% means 73 divided by 100. So to get that 100 out and actually write it as a percentage, we always take that step there, multiply by 100%. And that gives us the figure that we're going for. And so that's why we did that step here as well. Well, let's practice out a couple more just for the sake of more practice with the numbers if they get slightly weirder. And this one is a little bit different because it started out with a percent. So part of it's already done on this problem. So we already have 44% is given. So all we need is now the simplified fraction and the decimal form. So either one is not too bad to go for. Let's go for the simplified fraction first because, that ties in with the definition of a percent in the first place. If you say 44%, then 44% in its most literal form just means it's a ratio with the denominator of 100. So we'll take 44 and divide by 100. But notice what we're really doing if we're making that happen. There's a decimal spot right here. If we move that back 2 units, that would give us the decimal form. Oh, but however, we're going for the fraction, so we're just about there. We want this fraction simplified, so we just have to reduce it down to get the end answer on this one. So in the fraction form, let's say divide the numerator and denominator by 4. That would give us 44 divided by 4 for 11. 100 divided by 4 will give us the 25. And so we have now 11/25, and this is simplified. So 11/25 altogether. So we have the percent given. Now we have the fraction. It's now a prime number divided by 5 times 5. So this can't reduce whatsoever. All we need now is the decimal number. Anyone happen to know what this would be just as a decimal?
0.44.
Yeah, absolutely. Really, that's kind of what we're doing over here, right? If you go back to the calculator, let me dismiss that warning. Rewrite this as 44 over 100. You get exactly as you said, 0.44. But that's the logic of any percent. The decimal point is here to start, where it's highlighted in yellow. If you divide by 100 because it's 44 over 100, all you're really doing in practice is shifting the decimal 2 spots to the left. So this becomes 0.44 as a decimal. So there's the 3 different forms of the number for part B. A little bit less work on this one because the first portion was given, the percentage. Let's try that one more time with this one, 25/15. Well, we've got the fraction 25/15 to start. This time, as opposed to part A, it's not simplified, so we take one additional step. We can divide by 5 numerator and denominator. So this would give us 5/3 altogether. 5 would go in there 5 times, and down in there 3 times. And now we have an interesting fraction. I mean, it feels different than 17/23, right? This is more than 1. Some people like to call this an improper fraction because the numerator is larger than the denominator. It's not improper in the sense that it's wrong. It's just a technical way we say numerator is larger. This represents more than 1 whole. But you know, as far as the instructions go, it's completely fine. You don't have to convert this to a mixed number or anything along those lines. I don't think MyLab would possibly even accept a mixed number. You're always allowed to just leave your improper fractions like this one exactly in that form. So this is simplified as an improper fraction. So now we need the decimal number for that and the percentage, but really that's just clever uses of the calculator to get those next results. Let's scroll down to this part as we get those next values. So you can either start with the original number, 25/15, or the simplified version. The calculator won't mind, and it's going to be equivalent either way you look at it. Let's work with the simplified version. As a decimal, 5/3. This one will be another repeating decimal like on part A. So we'll round this one to 2 decimal places is what it was asking for. Let me double check that in case I forgot. Yeah, 2 decimal places. So rounding this one to 2 decimal places will give us a 1.67. And so this is as a decimal. Now, if you gave me 167%, you shifted the decimal place 2 spots to the right, that'd be okay on a quiz and exam. But let's say for MyLab, let's be more careful on this and write this out by going this way. 5/3, now going for the percentage on this one, we'll take the figure exactly as it is in the calculator, then go times 100, copying the method we used in part A. Now we have more than 100%, but that's just because it was an improper fraction. 25/15 is more than 1 whole, 15 itself. And this one to 2 decimal places would be 166.67. And this is in percentage form. So that's our pretty rough rundown on this. And I forgot one symbol on here. To really express that it's in percentage form, a really good call here is definitely include the percentage sign, or else that number could have some different meaning. So the percentage symbol does tell us what the unit is, so it is important. So now, after putting that in, it is in percentage form. Well, any questions or comments at all, folks, running through any of these problems? Okay, so that's our warm up on this section, getting just started, thinking about percentages. This one is pretty weird, but so is the fraction. It was an improper fraction. This percentage might make sense in certain contexts, and it might not make sense in others. For example, a standard grade can never exceed 100%, say on an exam or anything like that. But if we're talking about a growth of something, say the growth of a economy of a country, like say USA, it's completely fine to say the economy grew by 166.67% over whichever time period we're talking into. So the context is going to tell us if this value makes any sense or not. And that's what we'll be looking into in the next problems. These are just random math questions. But for this class, the bulk of our problems all have context. We'll be using this formula right here for our percentage formula. And in example 2, it says, in the following statements, express whichever first number is given as a percentage of the second number. So we'll put that first value there. We'll express it as a percentage of the second number. So we'll throw that into the denominator. And because we're writing it as a percentage, we're going to still use that strategy, just go times 100 to get that value out. You know, I have some regret on how I wrote that out. Let me write this as 5/3 equals 5/3 times 100%, which equals 166.67, and then say is in percentage form. We kind of just buzzsawed through it in the calculator, but I think it's good to put that one step right there in the notes to just really convey that's us converting to a percent form. So with the same kind of logic, here's a couple random kind of problems, but now they have context, thinking about percentages further. So example 2, part A says, to start out, the full-time year-round median salary. Now, we should qualify that word. We're going to look into statistics later on in this course, so this is not a bad word to look into right now, just as a preview. Median is different from average. Median is saying the 50th percentile. You have to say what that means next, so it's kind of like a stack of definitions that go all the way down to median. So if you say the full-time year-round median salary for US workers in year 2000, that was a long time ago already, over a quarter of a century, if it's $30,846, and that's a median, what they're telling us is back in the year 2000, half of the population made more than $30,846, and half of the population made less than that value. So this is the value directly in the middle, the central value in that certain sense. So the 50th percentile is the center value. So median pay was $30,846 in the year 2000. Year 2020, I think this is when the book was published. That's when all their figures seem to come in. It was 52,800, so it's definitely gone up. We would wonder if it's gone up on pace of inflation as a separate whole question. Probably not, but it did go up. There's no doubt about that. So in year 2000, this is the median value. So half the people in the US for a full-time year-round salary made more than that and half made less. But what we're doing is putting this number into another context by thinking of it in terms of a percent. So following this formula here, the first value was the 30,000. The second value was the 52,000. So writing this out as a percentage, we can say the percentage is take 30,846, divide that by the $52,800. Nice thing about this setup is units will cancel on this, but let me also remind myself not to forget this step. I'll go, let's just match up the notation, X for times 100%. Now it's converted from a decimal format, which is just as fine as a number, into an actual percentage. So here it is as a rate or ratio, a fraction, and units will cancel off here, so dollars and dollars are gone. The only unit that'll be left is the percent symbol. So let's throw this one into the calculator. 30,846 divided by 52,800. I've been trying to be a little bit better on the notes on the rounding, so we don't have to have all those edits in red. This one will be rounded to the nearest tenth as needed. But when this rounding is indicated, it means the percentage is going to be rounded. So we don't round here yet. We'll round after we go times 100. So nearest tenth just means one decimal place. And we get a 58.4%. Well, we're done. That's the whole answer, 58.4%. Any questions about it so far?
I have a question, but it's a calculator question, really. So
Sure.
when I did the 30,846 divided by the 52,800, and I got the answer, and then I took the answer and said times 100%, it came out still as the same answer. Why was that? Just because I added the percent sign in is,
I think I see what you're saying. So you took this value here and then you
Mhm.
went, let me pull up another calculator where it looks probably a little bit more similar. This is a calculator that we can't actually use in exam settings, so it's one that I don't pull up very often, but sometimes just for the sake of visualizing what it might look in your calculator, it's not a bad idea. So this is the TI-83 calculator. And if you're using, say, like an actual scientific calculator, the TI-30X2S is the one I put in the syllabus. There's just a one small screen right here. Putting the numbers in this one, it's going to be 30,846 divide 52, 800. And yeah, it's totally fine to just hit enter right here. And then you said you went times and you saw A and S come up. Is that accurate?
that's correct.
Yeah, so when it says answer like that, it's referring to this line right here. So if you go times 100, it's
But I
always
also
going to
added
match.
a percent because
Oh,
in your equation you had 100%. So I did times 100%.
oh, how'd you get the percent in the calculator? I guess is my question.
Oh, it's got a little, it's in there. It's got a percentage symbol that I can put.
Oh, wow, I don't have one on this calculator. Let
It's
me look
on, like
into
you have to hit the second, like I hit, it's above one of the numbers.
oh, let me see if I can find that. So I have another calculator to look into. So I think in these notes, we pulled up a calculator.
On my calculator, if it helps, it's the second function of the first parentheses button.
Yeah, same on mine.
Yeah, right here on this one, there's a percent symbol. You know, I have to be completely honest with you. I have never noticed that button whatsoever. Let me see if it's on here. So I don't think it's on this calculator, actually. That is pretty weird. But I'm gonna have to look into that. You know, I actually have one of these calculators in a drawer somewhere. So let me grab one. Yeah, and sure enough, I see a percent symbol on this one. And so if I take that same operation, it's kind of hard to show here because I don't think I can just point this calculator at you and have it be seen on Zoom in a reasonable way. But if I match up what's going on Desmos, I would go here, 30,846 divide 52, 800. I hit enter and I have this value, 30,846 divide by 52, 800. There we go. So I see this value stored in the calculator at the moment, and now I'm going to hit second percent. And yeah, it looks like ANS percent symbol in that particular calculator. And hitting enter, oh, I got 0.0058.
Yeah, it
Strange.
didn't change it. That's why I was wondering because if I do it by 100, it works, but if I do it by 100%, it does not.
Yeah, this one's kind of weird. Let me see if I can try it a slightly different way. 3846 divide by 52, 800. Now my calculator, I really just have to go ANS times 100, and that should do the job. So if I go times 100, but let me say I put in the percent symbol. I mean, that makes sense. That's how it's written directly here, right?
Right,
So
that's
go,
what confused me. Because if you do it by 100, it comes out like you had it, the correct answer. But when I did 100%, it did not.
yeah, so I've got pretty much just verbatim this in my calculator. After putting this in, getting that number, So I hit the time symbol, ANS shows up, put in 100 and a percent, and it comes out as the same exact number. Yeah. So it looks like the roll of the percent symbol, when you do go to hit that, looks like all it's doing is dividing by 100. So when I put 100 here, it just canceled each other out entirely. So that's a good thing to keep in mind for the calculator. You'll just want 100, and then you have to include the percent just as copying it down, really.
Okay, thank you.
Yeah, absolutely. Thanks for asking about that. That's actually kind of confusing, trying to put this back into the calculator just as seen on paper. So a quick reminder on this. For this part right here, just copy. And the calculator, that percent symbol just seems to be dividing by 100 on any number I put. Let me test it. If I go on this same calculator and put in, say, 5. So there it is, hit the shift and the percent symbol. So 5% and hit enter. Yeah, I get 0.05. And that makes sense. That's a true statement. 5% as a decimal number gives you that. So it looks like if you're converting from just a number as a percentage into decimal, that's the purpose of that symbol there. But writing out the percentage, we would just want to copy the percent symbol itself. Or maybe thought in this way, if you go 584 in your calculator, 58.4, let's type that in, 58.4, do the percent symbol again, hit enter, and you get 0.584. And yeah, that looks like its roll. This symbol just seems to be converting your percentage into decimal format is what it's truly doing in the end of the day. So that could be useful, absolutely. But for here, we would just leave it in that format. Well, other questions about that so far? Okay. Still, when you look at this whole question, I would myself personally still have one big question about this. We're told the median worker pay was 30,000 in year 2,846. Don't want to short that amount. It grew to 52,800 in year 2020. And we got a percent, 58.4%. But the biggest thing we want to kind of wrap our mind around is, what does that have to do with the context? So even though this is not part of the question being asked, it's a good idea to kind of do a sanity check or a smell test on this number to see if you can make sense out of it. So let's put this into context. This says that the median pay in 2020 was 58.4% of the median pay in, oh, hang on, 2000 is where I should have started. Sorry about that. In year 2000, so the lower amount, that figure was 58.4% of the median pay in year 2020. So that means it was the 2020 pay grew by a considerable amount. The prior pay was not quite 60% of it, just a little bit more over half. So I'll try to put this into these percent problems just as another way to double check that. But does that make sense with the percent so far, seeing it in this context? Okay, let's try out another one before we get into the other problems. This one is also about the USA, but this one's different. It's about nuclear weapons, so kind of a more concerning problem. It says the United States has an estimate 5,550 nuclear weapons. That's definitely an estimate because we don't know how many of these weapons might be classified and just not listed anywhere that's available to the public. This is out of an estimated total 13,125 nuclear weapons worldwide. And that's also an extremely vague estimate. We're going to have to rely on the CIA to do a really thorough job to track every single possible nuclear weapon. That might be a very hard figure to estimate as well. All we're doing is rewriting this information now in terms of a percentage altogether. And I agree with Echo. This is kind of one of the things people refer to in foreign policy is really shotgun foreign policy, where everyone's pointing a weapon at each other, and the world just seems to march on because everyone knows if a weapon does go off, everyone kind of loses. So that's our basis of foreign policy as it relates to nuclear weapons. Political science is a scary subject just because it has to touch on this kind of stuff. Well, if we can think of this in terms of a percentage, what's going on, that gives us another idea what's going on with these values. All we're doing in this problem is writing the statements, expressing the first number as a percentage of the second. So we'll start with the estimate 550 nuclear weapons that USA has. The second number is the 13,125 nuclear weapons, very rough estimate worldwide. So as a percentage, we would say that this is equal to 30,846, or excuse me, that's the wrong number, 5,550. My eyes were definitely looking at the wrong spot, nuclear weapons, divided by 13,125 nuclear weapons. Just like with the problem over here, the units completely cancel out. And all we're doing now is considering the fraction. But don't forget, go times 100%. And again, thanks for asking about that weird vague issue in the calculator. Definitely leave off the percent symbol. All we'll be doing is writing down times 100 and then copying over the percent symbol in the answer. So back over here, it'll look about like this in your calculator. 5550 divide by 13125, except it's probably a sideways fraction, read left to right. You can either hit enter now or just go times right away as it stands, 100 if your calculator allows. And this one's rounded to the nearest 10. So this will be 42.3 as a percentage. So we've got it. The percent is 42.3%. But what's the interpretation? Any volunteers to say, what does this number really mean in context? What would you all say 42.3% means in this problem?
That means that the United States has 42.3% of the world's nuclear weapons.
Yeah, exactly. Almost half. That's kind of crazy when you think about it. If these numbers are reasonable estimates, we are armed to the teeth, is what this is saying. So let me put down, as to the best of my ability, verbatim what you said. This means the United States has approximately 42.3% of the world's nuclear arsenal. That deserves an exclamation mark. That's not something I would have really known on the back of my mind. That's not thoughts I walk around thinking about every day as we go. But that also tells us why political science and foreign policy are probably worthy subjects to kind of pursue, because we've got to kind of make sure there's amnesty among nations when there's so much firepower out there. We happen to be holding a huge amount of it. Yeah, absolutely, Echo. The US has 42.3% of the world's nuclear weapons. Yeah, that's kind of a crazy figure when we think about it. Well, this is our look into percentages, kind of similar to what we did in the example one, but now our numbers have context. We'll be delving into this a little bit further in the next part of the notes. But any questions or comments so far with where we're at? Okay. Well, sometimes percentages aren't just meant to be a part of a whole. They're meant to convey how something grows or how something shrinks. So change from one year to another, for an example. And that's when we start to get these kinds of formulas in the notes. We'll be looking at two types of change: absolute change versus relative change. And just like before, we'll look at this on a couple scenarios. And these formulas are important enough. We'll look into it on another example after example 3 as well. First, absolute change is kind of a nice one to think about. Absolute change just tells us how much did we increase or how much did we decrease in a quantity year after year. So it's going to be thought in terms of the new value minus the reference value. And the problems that we're looking into the book and the problems I assigned in the homework, as well as the lecture notes, reference value is usually a value from the older, I want to say, date. So if we're looking into the total student loan debt in the United States, we're told it increased from $1.06 trillion in 2014 to $1.57 trillion in the year 2020. That's only 6 years. But the older date, the 2014 date, is telling us that's what we mean by the reference value, what it was before. And even though we're long gone from 2020, we're going to think of this as our new value. So that's what absolute change is going to be all about. However, this section is really about percentages, so absolute change is not the whole story. You can get a feel for the magnitude of an absolute change if you put it in terms of a percent. And that's what the relative change is all about. We have now this in terms of percent. We'll take the reference value here, divide by it. And so that means the numerator is just absolute change. Divide by the reference value, multiply by 100, and now we have a percentage, which gives us an idea for the size of the value we're going to be looking into. So that's what we're going to take a look into in the next couple questions. I want to do these questions kind of carefully because there's always a little bit more going on than expected when it comes to percent. So trying to do it in about 3 minutes and some change is probably not a good idea. So we'll come back to this example here when we're on Thursday's lecture. But any questions or comments so far with the definitions or formulas? Okay, we'll end class here just a few minutes early once again, and take a look into these problems when we come back Wednesday. But once again, thanks for your hard work and participation thinking about these problems. And I appreciate all the questions and suggestions people put out. And thanks for the discussion on this one. I never knew about that percent symbol, so that helps out a lot. I'm very happy to talk about those topics. But have a great night, folks. We'll be back to it on Thursday. Thanks.
Thank you.
You bet.